Okay, for our special colloquium today, our speaker is Dr. Dale Gary from the New Jersey Institute of Technology, where he's a distinguished professor in the Department of Physics, and he's talking today about the FASR, Frequency Agile Solar Radiotelescope. Thanks.
Great, thank you. Let that respond to it. Okay, yeah, thank you very much for inviting me. It's a great pleasure to be here. I'm going to tell you a little bit about the Frequency Agile Solar Radiotelescope. This is a concept for a future instrument that has been around for quite a few years. I'm actually going to give you some historical context of where that concept came from and what it looked like when we were really ready to build FASR, which was about 10 years ago or so. Unfortunately, we didn't get it off the ground at that time, but one of the things that happened was that we got some of the era funding from the financial crisis in 2009 to build a prototype of FASR, which is the Owens Valley, the expanded Owens Valley Solar Array. So that has allowed us to prove a lot of great science that FASR would do. And so I'll be talking to you a little bit about some of that science and hopefully pique your interest in what this kind of technology can do. Then I'll talk about, because EOVSA is a prototype for FASR, I'll talk a little bit about what we learned from EOVSA and how it should be applied to FASR. Then I'll talk a little bit about updated FASR design parameters. You know, technology has moved on since 2009, so we have a lot of advances that can be used to do a better job than what we were anticipating back then. I'll show you a few simulations, nothing too elaborate, but just to whet your interest in what FASR might do. Now, these are science topics for the sun, but FASR can be used for non-solar topics as well. We had some discussions this morning about that. So I'm happy to take questions or hear ideas from you about how FASR might be used for non-solar as well. And then I do want to point out that we'll have a FASR design workshop in a couple of months at NJIT. And so people are interested in learning more about the project and also contributing to it with discussions and hearing your expertise and your knowledge. We certainly invite you. There are, we have some funding available for travel, things like that, if you need that. So, the FASR process is a long one. We actually, our first meeting was back in 1995 in San Juan Capistrano, where we talked about the Solar Radiotelescope, SRT. And that was prior to the 2001 Astro Decadal. And at that time, we began a series of solar and space physics decadals. So prior to that, there hadn't been such a thing, but the solar and space physics decadals now come every like 2 years after the astronomy. So there was an interim report in 1998 about ground-based solar facilities where FASR was presented and was recommended for development. And then in 2001, we went through the Astro Decadal and also got a very high recommendation for FASR. And then we had the 2003 Solar and Space Physics Decadal, where we were the top priority in small projects, less than 300 million. The cost at that time was around 50 million, I believe, is what we were thinking. And then at around that time, we had our first FASR workshop, which is right here at Green Bank. We had an international group of people come and talk about the design. A lot of folks from NRAO and elsewhere talked in great detail about the design. We really accomplished a lot there. We got to a point where we were ready to do some planning. So we got some funding from NSF to do site surveys and things like that. And we were did an operations and maintenance plan at that time. And then our first real opportunity to propose came in 2008 because the Astronomy group in geosciences at NSF had created a mid-scale initiative, which was one of the things that was suggested in that 2003 Decadal. And so we proposed for that for 25 million. It was actually a scaled down version of FASR, but that was declined. And then the ERA funding came along. We got the funding, $5 million to build EOVSA. So that was in 2009. We actually were a little bit late getting started with that, unfortunately, because we weren't that familiar with this sort of thing, but we learned that we had to do cultural surveys and biological surveys and pass the environmental protection hurdles. So we didn't get really started until about 2012. EOVSA was completed in 2017. So we've been operating since then with EOVSA. And it's a pathfinder instrument. It's about 10% of FASR. So that's I'll be telling you the science that we got from that. By now, we're into the 2010 Decadal. We got a recommendation for FASR mid-scale funding. In fact, FASR was one of the projects that was used to argue that mid-scale initiatives were coming along and that they needed to be funded. So asked NSF to come up with a mid-scale program. In 2013, we had the Solar and Space Physics Decadal, where once again we were a top priority mid-scale project. And so we submitted a couple of other proposals, 2014, 2017, both declined at the white paper stage. The 2017 one, in fact, included greenback. We were going to build a prototype of the 6-meter array here at Greenback. Then this mid-scale infrastructure industry program came out at NSF in 2018. We proposed in 2019, again declined. So that decade was a pretty miserable decade for us. However, some things have changed, I think, this time around. We did go through the Astro 2020 Decadal, and at that time, it was the radio panel said it recognizes FASR as a missed opportunity that has not been fully implemented despite past strong endorsements. In addition, we have all the science I'm going to tell you about from EOVSA that really impresses the community. I think the community is ready, realizes now that what the opportunity that they missed. So in 2021, we had a virtual workshop, and we're having a second workshop now in 2023 in January. It's the one I mentioned, to which you're all invited. And so what we plan to do is in 2023, we're going to do a small upgrade of EOVSA, add another couple of antennas. But in 2025, put in a FASR MSRI proposal, at least to do a study to finalize site selection and things like that. I guess the reason that I was asked to come here was because of one of these decadal survey white papers that I had submitted about FASR. And in fact, there were a lot of white papers submitted about FASR. These are all the science white papers that we put forth for the solar and space physics decadal, involving the quiet sun, active regions, solar flares, coronal mass ejections, which I'll describe in a bit. Just looking at this middle corona, which is a region, not really close to the sun, but not all the way out to Earth. It's just middle range, which FASR has a role as well in play. Of course, space weather, and even beyond the sun, we're talking about applications of this kind of work to other stars and possible influences on exoplanets, etc. So, so FASR was developed over about 6 years, from 2003 to 2009. A lot of organized effort with the goal to, I can look here, but so to build a spectroscopic imager capable of addressing all solar radio science from over a very wide range, from 50 megahertz to greater than 20 gigahertz. And the design called for 3 different arrays to cover that broad range. There was FASR A, B, and C, going from high frequency to low. So A was from about 2 to 20 gigahertz, and then B was these are the frequency ranges here. So I guess A was 2 to 21, B was 300 megahertz to 2.5 gigahertz, so there's a little bit of overlap. And then FASR C is the metric radiation from 50 to 350 megahertz. And you can see the number of antennas we had planned, like 100 of the smaller ones. These are 2-meter antennas, 60 of the 6-meter, and 40 of the low frequency, which would be log periodic dipole. So this was the plan, but you'll also notice that we wanted to do this time resolution of 1 second, covering the whole frequency range with 500 megahertz per channel. So that was what we thought we could do easily at that time. So 500 megahertz IF. Nowadays, we could do a much broader IF. We could certainly go faster. And at that time, we were talking about 2.9 kilometer by 3.8 kilometer array on the ground. I think we'd like to do a little bit larger than that, but not significantly large. So despite several attempts to get funding, including various D-scopes, all of the proposals were declined except for this 10% sort of FASR pathfinding EOVSA. So I do want to point out that a solar array really needs certain specific characteristics because it's looking at a unique object, right? So we need to have the UV coverage image of broad, highly complex source of about a degree across, and with sufficient resolution down to about 1 arc second at the high frequencies to cover all of the spatial scales. Again, we want to measure a very broad spectral range because all parts of the solar atmosphere are participating in activity, and also we just want to be able to study the various layers of the atmosphere. And we want to do that very quickly because the sun is a very dynamic object. At this time, it's 1 second or less, and we would need to go much lower time resolution at the highest frequencies. We'd like high frequency resolution because, especially for coherent emission, you get very fine structure in the spectrum. And we want to be able to measure the high flux density from the sun during solar flares without saturation. And we want to be able to cover the very, very rapid changes. So the sun is very dynamic at times. So item 1 impacts the antenna sizes. So we actually need to scale our antennas so that we are sure to see, about a degree across. At the highest frequencies, we go ahead and come down to a ½ degree, simply because at the highest frequencies, most of the emissions can be limited to the sun and not so much to the outer corona. Item 2 dictates broad front-end bandwidths, so at least 10 to 1 feeds, and also broad IF bandwidths for rapid tuning. So you can do either one, but we need to cover that range. Item 3, the high frequency resolution is pretty easy with modern digital hardware, so not really an issue, except that of course it impacts the data volume. The finer your frequency points, the more data you might And then item 4, covering the very bright emission from solar flares, et cetera, requires a stepped gain control with low latency running. So those are some of the requirements. Let's see, I have a transition there, but so this is the EOVSA array as it exists now at Owens Valley in California. You're looking at 7 of the antennas. One of them is way back in the back. This is our most distant one. If I can show up for a moment. So way back there is one. So that's about, it's covered about a square mile, but with just 13 antennas, so it's a very sparse array. But it does have the ability to provide 1 second imaging on that broad range. And this range, by the way, is 1 to 18 megahertz. So this would be the FASR A highest frequency component. So I just thought I'd tell you a few words about solar radio emission mechanisms, so that you're aware of how the sun is producing the radio emission we'll be talking about. Of course, we always have free emission from Strawman, where the electrons are making distant collisions with ions and producing radio emission that way. The important thing about that is that you need those ions there, right? The electrons have to have something to interact with. And so it depends on the square of the density, which is also the way X-rays respond. And so I'll be contrasting some of the radio emission with X-ray emission. And just keep in mind that both this mechanism and X-rays require sort of lots of rather high density. The other one, sort of key one that we're going to be looking at is gyro emission. This can be either line or continuum emission. So at very low energies, you end up with a cyclotron line. It's basically the B cross B part of the Lorentz force is producing a very pure line emission. But if you include electrons of any energy at all, like the solar corona is 1 million degrees, so it's producing harmonics of that due to this relativistic effect of beaming. So shown here, so you end up with this forward lobe being stronger than the backward lobe, and that produces harmonics that come in as frequency is S times the gyro frequency, S being a small integer, 1, 2, or 3. For the solar corona, we get up to about S equals 3 for this mechanism. And so this would be important in active regions and places where there's some strong magnetic field strength. But for solar flares, now the electrons are mildly relativistic. So we have something called gyrosynchrotron. It's not quite synchrotron, which requires highly relativistic electrons, but in this mildly relativistic range, you get harmonics that are maybe ranging from 10 to 100, and this produces not line emission, but a continuum emission. So the lines are broadened and blend together, and you end up with them. Okay. I do want to also mention coherent emission. This is effectively narrowband emission. This could be due to a collective action of the electrons, like plasma oscillations that are going to produce emission proportional to the square root of the density, the electron density. And there are a number of different types of bursts, like types 1, 2, and 3, famous solar burst types that are clearly due to plasma emission, but there are other kind of unusual burst types which we expect to be due to plasma emission as well, but it isn't. We have other types of waves like Whistler waves, which are responsible for generating electron cyclotron maser emission. And again, that's very narrowband emission. So looking now at the gyrosynchrotron emission mechanism, this is this broad emission at harmonics of 10 to 100 or so, and it makes a broad spectrum, and that spectrum changes with different parameters. So I just want to show you a movie of the spectrum. As we change the magnetic field by a factor of 2, the whole thing just shifts to a higher frequency. Here we're changing the number of high energy particles. Here we're changing the energy of those particles. And here we're changing the line of sight direction to the magnetic field. Here we're changing the thermal densities. Here we're changing the, think of a power law distribution. That was the low energy cutoff, and this is the high energy cutoff of that power law. So all of these different effects cause shifts in the position of the spectrum and changes in the shape of the spectrum, and they're very well known. They're very easy to characterize in terms of these parameters. So by measuring the spectrum, you can actually do a fit to obtain those parameters from the fit. So that's the important thing. Notice that the dashed line is the O mode, the solid line is the X mode. So these are the two magnetoionic modes that are produced in the plasma. And the fact that they are not on top of each other means the angle of the direction of the magnetic field is not 90 degrees. If it was 90 degrees, they would be the same. So when they when you go to more looking along the field, the dashed line one sort of goes away so that they separate. Now, this is a brightness temperature spectrum, and these are reasonable numbers for solar flares. So the brightness temperature is, the peak of this is several hundred million Kelvin, right? So that's not an actual temperature. It's due to the non-thermal particles. It's the effective temperature of those non-thermal particles, mild electrons. If you have spatial resolution, you can make that kind of measurement. But normally, up till now, historically, we have not had spatial resolution to image the flares and get this kind of spatially resolved brightness temperature. Rather, we had flux density spectrum. So this is showing you if we take a bunch of different, it's this sort of spatially relatively resolved spectrum, but now you add a bunch of them up because you're looking at a source with multiple sets of these parameters, and it produces the blue curve, which is a flux density spectrum, where you have now lost the diagnostic potential that is provided by the brightness temperature spectrum. So the flux density spectrum that we've lived with all of these years, you can interpret that in various ways to learn something about some of the parameters, but you really are not diagnosing the parameters point by point. But that's what we can now do with EOVSA. So this is a dynamic spectrum showing a solar flare. This is a very famous, very bright solar flare that occurred in 2017, just after we got EOVSA running. And this is time going this way. It's about an hour. And frequency in that diagram at the top is going from it's actually 3 to 18 gigahertz. And you can see the different colors there are just the flux density as a function of frequency. So you have that strong increase during the impulsive phase, and then you've got another peak over here. And see, I'm already running my movie. So over here are images taken at multiple frequencies and multiple times, so that you'll be able to see where those things are occurring. And this line here at the edge is the solar limb, right, the edge of the sun. So this is an event that's sticking out from the sun. And then in the far right is an extreme ultraviolet image, or movie in this case, that shows an erupting, you can see that kind of tennis racket looking loop there, and that thing's going to shoot off to the right, or erupt from the sun. So if you watch that, watch the radio emission, you can see it's growing higher and higher over time. It's expanding, And it was changing color there, and that's because this is what I call a false color diagram, where I'm actually combining frequencies. So the high frequencies are colored blue, the low frequencies are red, and intermediate frequencies are green. And so you combine all of those in a true color image, and you can actually get a feeling for the different frequency components. Let me just show you that one more time. And you can see that it gets very blue there toward the peak. And that means that the high frequencies are very, very dominant. You can also see that in the spectrum. Okay, so EOVSA then uses something called imaging spectroscopy. So this is a bunch of images at one time. We actually have more images than this. It's just a selection of them. And you can see that at the highest frequencies, it's trying to make a loop. You know, you can see it's sort of a loop-like structure here. At the intermediate frequencies, it becomes the loop top. So the emission is dominated the loop top. At the lowest frequencies, the whole loop is emitting, but it is becoming a larger source, but also our resolution is dying, right? So we're starting to get a lowering of the brightness. Nevertheless, if you take this set of images and put them together as a data cube, and now look at different in that image, ask what is the spectrum at these different locations. This is just one of the frequencies, just to find out what pixels you're looking at. You have 4 different examples there. You've got one that is somewhere in the middle of the source, and it's got a relatively high peak. You can see that the spectrum is rising. It looks similar in shape to what I showed in that earlier movie. And there's also a fit to that. There's a solid line there that's fitting those points. And these are the magnetic field and index, power law index of electrons that are producing those emissions. Then if you look at this one, you'll find a similar spectrum, shifted a little bit. But now as you go upward in the corona, above the bright stuff, you start to see the peak shift quite a lot. And with that shift in the peak, the fitting of the spectrum indicates that the magnetic field is dropping. So you're getting a magnetic field as a function of different positions. And so this is the diagnostic power of the brightness temperature spectrum. Yes.
Sorry about this. What is the angular resolution on, like, so let's say that 1 meter?
So we go from about 3 arc seconds at the bottom, and it just goes. So it's about 5 arc seconds, 50 arc seconds at the top. I don't have any arc second scales actually here, but I have some other solution there. So, okay, we can do this at 4 points, but the point is we can do this at every point in this image. We can get similar spectrum in every pixel, and we can do this at every time. So we can make movies not only of the emission from the flare, but of the parameters that are fit from the spectrum. So I'm going to show you a couple of movies here. This is a science paper in 2020 and a Nature paper in 2022, where we described what we learned from this flare. These different blocks here are different pixels where we measured these spectra, and what we're plotting here is a magnetic field in this plot. So the one on the left, people online. So this is the magnetic field as a function of position, and then if I play the movie, you can watch that develop over time. And what you'll notice is that the colors get darker and darker blue over time, over the whole region. So what this is saying is the magnetic field was quite high at the beginning. There's a color bar, it's a little hard to see there, but it was 800 Gauss or so at the beginning, and then braided down to almost 200 Gauss at the end. So there's a decay of the magnetic field over time, over this whole region. At the same time, this is a plot of the energy of the particles where the yellow or the orange is thermal particles. And there's a big hole there. There's a big kind of crescent-shaped hole. And inside of that hole are where the non-thermal particles are going to show up. So let me play that movie. And you can see in blue, these non-thermal particles start to show up. So there's like an insulated place in the corona where the particles are all very high energy and there are no thermal particles there. So the flare is producing these very, very high energies in that location, almost with 100% acceleration efficiency. So there's no thermal particles left. Now, if you watch the bar panel here, those contours are indicating that where the boundaries of that hole, and you can see the extreme ultraviolet loops are growing with time, and that hole is maintaining its position but moving outward with those loops. So all of this is brand new, obviously. Prior to this, we had no idea what the magnetic field strength in flare was, let alone what the magnetic field strength of the function position was or how it developed in time. So this is another view of the same flare. Now we've rotated it to be vertical. We can make a model, a magnetic model of what the magnetic field looks like. And this brings us to something called the solar flare, like I said, standard solar flare model. And the idea is that you've got a flux rope forming. This is a current carrying loop, and it forms very low and then rises very quickly. And you see it getting ejected due to this buoyancy force that's just firing it out. And as it rises behind it, the magnetic field is brought in behind it, and the magnetic field is oriented oppositely on either side of this line. So it's going up on this side and down on this side. And those oppositely directed fields, as they come together, undergo something called magnetic reconnection. They actually reconnect, retie, if you will. And so these lines that are going vertically become pinched off. One of them comes down, becomes part of this arcade of loops. And one of them, the other end, zips up there and becomes part of the flux rope. And the flux rope then rises due to that buoyancy force. The way that we used to learn about this stuff is through the X-rays. So the X-rays are here. This is thermal X-rays, and the blue contours there are the non-thermal X-rays. But this can only be done at various, at kind of crudely at different times with very little energy resolution. This is a very hard measurement to make, and the reason is because there aren't very many particles there. And remember, X-rays require particles. But now with the radio emission, we can now look at the radio emission all through that column. We have radio emission everywhere along there. And it's very dynamic. We can do this on a second by second time scale. So at this moment in time, the flux rope is still there, trying to head out. We've got all of this emission in the radio along there. At each of those 6 locations indicated, we have spectra, which we can fit with the solid lines. And by doing that, we can measure the magnetic field as a function of height along there. And this way over to the right is the magnetic field as a function of height. I can find my pointer right here. So the magnetic field is going from 0 to 1,000, actually 1,500 Gauss here. Very low heights, it's very high. And then as you go to higher heights, it actually reaches a minimum, and then it goes up a little bit again, and then goes down. And these solid lines are actually theoretical fits to what should happen according to our best understanding of what's going on in the connection. So we're actually measuring this profile and seeing exactly what the theory is expecting. But what's nice is that we can now take our models and tweak them to match this, and then learn something very, very quantitative from the models. Now, maybe I'll leave that there. So that's a gyrosynchrotron emission. I mentioned coherent emission as well. This is an example of a flare where we saw some coherent emission. You can see very clearly where the coherent emission occurs. This green time profile is the time profile at one frequency through there. And it's obviously very dynamic in time. It's also very bright. It's about 10 times brighter than it's a log scale plot than nearby continuum emission. And so now let's zoom in a little bit there. By the way, the very fact that this is here, just from the frequency, we can identify what the density should be. Assuming that this is plasma emission, this is the expression for the plasma frequency, to be 9,000 times the square root of NE. And so we can take our measured frequency and determine what the density should be, and it's about 4 times 10 to the 11 per cubic centimeter. Just a number, but it's a very high number. It's a number that's much higher than we would expect for most solar flares, at least at the heights where this is occurring. So it's a surprising number. In fact, it's hard to understand how we can get this emission out because it should be covered up with free absorption. It should be totally absorbed and not be able to escape. So there's a mystery about how this emission even gets out. If I zoom in though on a piece of this, you can now see each of these sort of bars is 1 second. So this is the resolution of our imaging. So these are 1 second. And you can see some fluctuations in frequency there. And if you look at those as a spectrum, these are the spectra at different frequencies at those 4 different times. Sorry, at all frequencies at those 4 different times. You can see the fluctuations there. And that's reminiscent of something called the zebra pattern burst. We've seen this before at lower frequencies. It's rare, but not that rare. And it's just causing these interesting line emissions that are moving along in tandem, varying in frequency at different times. And this is only 1 second of time. So this shows you the high time and frequency resolution that you need to resolve this. But again, you get these interesting spectral features, and it looks like that's what's happening here. Nobody expected to have such a thing at such high frequency. The interpretation is that if you take the frequency of each of those, it's just the oscillation number 1 to 5, and you look at the frequencies, you can see they make a nice pattern. They're obviously the separation in frequency is increasing. And this is thought to be due to something called the double plasma resonance, where you've got density decreasing upward, so that the plasma frequency is also decreasing upward. You've also got the magnetic field decreasing upward at some other rate. You know, it's got a different length scale. And where those two have a double resonance, so where the plasma frequency equals a harmonic of the gyro frequency, you can have enhanced emission. So this is the idea. So if you assume that the plasma frequency is changing by some scale length, so the density has a scale length L sub n, plasma frequency is going as e to the minus h over 2 Ln. And then you've got a similar exponential fall off of the magnetic field with some scale height Lb. Then, and this is from Kuznetsov and Sapp, a paper, theoretical paper about this. The separation of frequencies in adjacent harmonics divided by the frequency will depend on those like this. So let's go ahead and plot those. These are that function, the separation of frequencies divided by the frequency for those different oscillations, and they fall in a fairly linear way. And I don't have error bars here. I do need to go back and do this more carefully with error bars, but the nice thing is that you can try to fit that slope, and that sort of sets what ln over lb has. And the green one there corresponds to ln over lb of 2.25. The orange one is ln over lb of 2.20. So that it's actually very sensitive to find the location of that. Once you have that, you can identify what the harmonics are. So the gyro frequency harmonics at the high frequencies, it's S equals 7. At then it becomes 8, 9, 10, 11. So these are adjacent harmonics of the gyro frequency. Now we can go and image these things and find out, where those magnetic fields are. So this is the image of the flare at one particular time during this emission. The main flare is here, so that continuum emission is there, and this gyro emission, the coherent emission is occurring at some other location. In fact, it's associated with a sunspot there. So there's high field strength there in the surface, and of course it's falling off as you go upward. So I won't say too much more about this. It's a work in progress, but the brightest temperature of this coherent emission is very high. It's about 547 megakelvin. In other words, 47 half of what is that? Yeah, anyway, almost a billion. And the peak brightest temperature of the regular gyrosynchrotron part of the flare is about 57. All right. So there's some real discoveries available from the very high frequency and time resolution of EOVSA, plus the fact that it can combine imaging and spectroscopy. It allows us to do this diagnostic. EOVSA can also make full disk images of the sun. These are part of our pipeline that produces these images once a day. These are actually integrated over the whole day, like 8 hours, and some frequency integration as well, because of the fact that we only have 13 antennas, so it's a complex source, so we need to get all that UV coverage by doing this synthesis. But it still produces pretty nice images. The lower right image is actually from a spacecraft. This is a extreme ultraviolet image. That's nothing to do with radio, but you can see that the features are very, very similar. But we have limited dynamic range, so when there are sunspots, there are no sunspots here. This is all enhanced emission in various places where there are old magnetic fields, but there are no sunspots. But when you put a sunspot in there, then you get this kind of thing where our dynamic range just doesn't let us image the disk in the presence of these. These are saturated strong bursts or strong spots. It's not a burst, but just quiescent emission in sunspots. So this is that gyro resonance emission. But we can't do the full disk very well. It takes a long time to create that, but we can do active regions. And so this is these sort of green images here are from another radio instrument called the Siberian Radioheliograph. This is a new instrument that's just been upgraded from the previous instrument, and it does some very nice images. It has lots of antennas, like 200 and some antennas, but they're in a regular Grady kind of array, regular spacing, and they have limited frequency range and also limited spatial resolution. But this is an overlay of our images after correcting for solar rotation. The contours are EOVSA. And then this is an overlay of all of the different frequencies for this particular same active region for EOVSA. So the dark red are low frequency, going up to blue, although here the highest one where we see this, I should say these are at a particular cutoff. Okay, thank you. These are at a particular cutoff brightness, and so those high frequencies don't show up there. And then what I've plotted here are converting these frequencies into magnetic field strength using this simple equation that we're assuming that it's the third harmonic of the gyro frequency, and we can convert frequency directly to magnetic field. So we actually get a magnetic field map. Yeah, I guess I'm running out of time sooner than I thought. This is some modeling we did for this. I won't go through the details here. One thing I might mention here, the model produces a very high resolution. This is radio emission calculated from the model, right? So this is the expected set of contours at different frequencies from the model. This is the observations, and this is the taking this model and observing it with EOVSA, for example. So these should agree. They don't actually exactly agree. They're pretty similar, but they don't agree exactly. And that's one of those research areas where we're going to try to understand what about the model is wrong, and we'll make some adjustments to it. But if we were to image this with something like FASR, this is a simulation with FASR, we would have very, very high quality images from that. These are some observed spectra with EOVSA, just showing some of the diagnostics from this kind of spectrum. So the flat part of the spectrum is optically thick, and that gives you the coronal temperature, 2 million degrees. The falling part is optically thin, so the fact that it's falling very steeply proves that this is gyro resonance emission and not some other kind of emission. And the peak frequency allows you to calculate the magnetic field in that pixel, and you can do this at all the different pixels. But if you look at the model itself, you see other features. So you actually end up having an increase in brightness as you go to higher frequencies. So that would be an indication that at lower depths, the active region is hotter. This is a heating model that we part of the modeling we put in. You also see these sharp drops featured in the spectrum. Those are the harmonic structure from the second harmonic and the third harmonic. And you also see this near the -2 part of the emission, which is the free emission at higher frequencies. So FASR would allow us to do much better spectral resolution, much better in terms of the details of the spectrum. So EOVSA does great science. Why do we need FASR? Well, EOVSA's got 13 antennas. It's optimized for flares because flares are small and compact. It's like the easiest possible imaging problem, but its dynamic range is less than 100 to 1, quite a bit less in certain cases. Whereas with FASR, we would exceed 1,001 and produce much higher quality spectra. For active regions, EOVSA does one a day. For active regions, we could go a little faster, but FASR will be able to make snapshot images of very, very high resolution and high quality. So we'd be able to measure detailed movies of the active region dynamics. And one of the important things is coronal mass ejections. These are one of the most impactful types of influences that the sun has on the Earth. It's a bubble of magnetic field that leaves the sun, and when it strikes the Earth's magnetosphere, it causes auroras and geomagnetic storms, and can actually threaten technological systems. And those things are not visible from space because you have to put an artificial eclipse, right? You got to put a filter in front of the sun to see these very faint things. And they go off to the side, the ones you can see. What you want to do is see the ones coming at you. And FASR would be able to do that, would be able to image these things directly on the sun. I was going to talk about some design lessons, but I'm really running out of time. Maybe what I'll do is, let me at least cover this one. This is that strong flare that I was mentioning earlier, the September 2017 event. And as it went on, we put in steps of 2 dB attenuation, and this is the history of those 2 dB attenuation steps, and this is the resulting observations. And you can see that if we hadn't done that, we would have had, it was actually almost a 20 dB overall gain variation. So, but we would have saturated at 3 dB because our optical link, has a fairly low head rate. So we had to do that sort of thing in order to be able to do all this great science. I think I'll have to skip some of these things. I do want to mention this one. EOVSA works because we can do calibrations with a 27-meter antenna on the site that is equipped with a low, a cryogenic receiver. And so these 2-meter antennas, 13 2-meter antennas, and they're also room temperature receivers. They don't give you enough gain to image directly unless you pair them with a large antenna. So one of the great advances with EOVSA was to be able to get good calibration using this large antenna. And these use 6-to-1 feed horns designed by one of Sandy Weinrep's students. So this is the high frequency feed from 3 to 18 gigahertz. This is the low frequency one from 1 to 6 gigahertz. And so we use those. We need this apparatus here to move the 2 feeds in and out, and also rotate to correct for that was a very important design element. We hope to prototype a new 20-to-1 feed. This is from Jonas Flygare. He's now working with Owens. So updating phasers design, we clearly this 12-year-old design needs updating. The 325 megahertz that we're using in EOVSA can be enlarged greatly, possibly even allowing the processing of the entire 20 gigahertz band at once, either with very broadband systems or narrower band, but in parallel. The time resolution can be greatly enhanced, from 1 second to maybe certainly a tenth of a second or even less. The target frequency range, particularly the high frequency limit around 20 gigahertz, could extend higher to improve flare science. Definitely would like to go higher. Antennas can be cheaper. We may be able to increase the number of antennas without undue cost. Given more antennas, you can have a longer maximum baselines. You can have a denser inner array, which is needed for the full disk imaging of the CMC. This is a straw man design. So this is what was in the white paper, but this is by no means the final design. So we suggested maybe 4 gigahertz per channel instead of 500 megahertz. Time resolution of a tenth of a second at least, possibly higher. Somewhat larger number of antennas, but many of the other things are very similar. Okay, let me skip that. Just mention that one possibility we're thinking about now is to put phaser together with this DSA 2000 array that Greg Allen is starting to work on. This would go into a site in Nevada, but that by no means has been decided. And then these are just some simulations of arrays and simulating flares and trying to get this high dynamic range. No real go through the details there, but this is the last slide. So we're having a phaser design meeting workshop in January from 11th to 13th. That's a Wednesday through Friday. So the first day will be an updated science discussion where we'll present a new science traceability matrix, which tries to connect the science goals to specifications for the instrument. On day 2, we'd like to have a detailed hardware discussion with some engineers who are aware of the latest technical advances and can maybe tell us where we're asking for too much or maybe where we're asking for too little. On day 3, then we would attempt to synthesize the first 2 days and come up with a design vision for FASR that would be sufficient to present to the solar and space physics Decadal. Given a strong ranking in the space physics Decadal survey, which will be in 2024, we would prepare our full design proposal in 2025, and then a construction proposal. So that would be the plan, and we invite all of you who are interested to join us at NJIT. We do have travel support, and there's a link here for more details, or you can just send an email to me. My email is bgary@njit.edu.
Any questions from the local audience first? Yeah.
I know you have spectral kurtosis running, RFI mitigation running online for EOVSA. Are you planning to do that with FASR, or do you have some kind of like improvement or element to it?
We're still, we would certainly try to fold that into the digital design if it's not, if things allow it to fit, because we do want to get the full resolution power anyway, and so power squared is the only other thing we need to get to that. And so we are thinking about adding that. I have to say that we measure it, but we aren't applying it. We haven't really. We actually have a graduate student working on this. Some of you may know her, actually. That's Stacia, we call her Stacia. She worked, I guess, on the Guppy instrument here. She
was a summer student.
She was what?
I think she was a summer student.
Yeah. She had mentioned. But we're because when you apply it, you better be sure you're not throwing away good data, right? So it takes some care. So we're measuring it, and we're not really applying it yet. All of the data I showed you is we just if there's RFI, we blanket. But we would like to get the
Right.
So I think you mentioned in one of the slides that the receiver's cooled, but I wasn't clear if that was on this larger
that's only on
calibration dish.
Yeah, that's only on the large.
Okay, so they would be uncooled.
Yeah, all of our receivers are uncooled, and they're quite high noise temperature. But then when we point at the sun, of course, the sun dominates anyway. So it's only for the calibration that we are concerned with noise temperature.
Yeah, I'm just curious if that new system that run the mass ejection events with models and the imaging, what kind of lead time?
Yeah.
In terms of protecting satellites or whatnot.
Right. So there's two aspects of that. One of it is we'd like to know more about the initiation of these events, because that's the best possible lead time, right? When you see them developing and they're about to happen. So with EOVSA, we can't do that because we don't have the dynamic range and the speed of imaging. But with FASR, we would be able to see relatively small changes in the configuration of the magnetic field, et cetera, that could lead to that. But once they occur, our lead time will be, they take about 2 days, 1 to 2 days.
Oh, just that one, okay.
So if we're seeing them on the way, we would definitely. But one thing that's important is that they're not all the same, right? Some of them are very geoeffective, meaning they produce a large geomagnetic storm, and others don't. And it has to do with that direction of the magnetic field. It's the same as with the flare model. So if the Earth's magnetic field is down and the cloud is up, they're going to be very effective. They're going to cause these reconnections. And so what's important is to be able to see the surface magnetic field configuration as this thing comes down and predict whether it's up or down when it gets here. So that's another aspect. It's not just
Jesse, do we have any questions online?
Not currently, but if anyone online does have a question, feel free to raise your hand.
Any more questions from the audience here? Okay, well, thanks very much, and certainly good luck with this project. It's a very interesting question.